Okay, now this section B2.4 concludes our journey through the thermal history of the universe, which we started with the nucleosynthesis, and then we jumped ahead to the time of the CMB formation or the CMB decoupling, and we are left now with a universe which is electrically neutral, so there's not a plasma anymore, and we are dealing now with some oscillations that we actually observe in the CMB as an imprint. And now the question is, how do actually structures form out of this? So we want to start out with the density perturbations that we see in the sky in the CMB, which we've looked at now quite a lot, where we see in the angular power spectrum the individual peaks of the acoustic oscillations. And from the temperature variations, we know that then therefore the density variations are relatively speaking at the level of about 1 in a million. And then we want to go to the more recent universe, where we see in the large-scale surveys structures forming which have density variations which go well beyond unity. And if you compare the density fluctuations in higher dense regions like galaxy clusters with respect to the intergalactic medium, you end up with a few hundred in terms of density, larger than the average density in the universe. And if you go even to smaller scales, that is galaxy size, there you start having density which are 6 orders of magnitude, typically larger than the medium that we find on average. Now, the structure formation, independent of what kind of initial conditions you have, proceeds initially in a linear way. I'm not going to derive the equations, you can look them up in all kinds of textbooks. But you find that if you assume that the perturbations are small to start out with, they will grow with the scale factor. And that's a thing which you can take away from this. So let's call delta, that is the difference of the actual measured or actual value of density with respect to the average density divided by the average density. That's a value which is smaller than 0 for underdense regions and larger than 0 for overdense regions. And this delta scales with the scale factor A. So that is, while the universe expands, you find that there's a growing mode in the solution that you find, where the density increases linearly with a scale factor. This is somehow, if you want to take an analogy, like in the free market or in the capitalistic system, where whenever some people have more money, it tends to also become even more in the future. And the same is where there's less money, usually that money gets depleted quicker. So the contrast gets enhanced. And this is due to gravitational instability, in the sense that wherever there's more matter, the gravitational inpull will be larger, and there will be more matter pulled in, which in turn increases the gravitational inpull, and so on and so forth. In the linear regime for small perturbations, this scales with A, but obviously this is not enough to get the structures as we observe today. But for the average density contrast that you find, this is something we can directly compare with, let's say, density fluctuations on a larger co-moving distance. And typically in the cosmology, there is a size which is the so-called 8 megaparsec co-moving distance size, which is used to separate the nonlinear from the linear regime, essentially, where you have nonlinear growth where galaxies can form and clusters can form. And so this value is measured, so that's the density contrast that is measured. That's the so-called sigma 8 value. And that's of the order of 0.8, a little bit larger than 0.8, but it's about a unity value. And that means that in order to get a density contrast of 0.8 at these scales, it means that you'd have to start with a sufficiently large value at the time of decoupling, because the baryons oscillate until the decoupling time. They cannot form gravitational potential, so the stabilities cannot grow really unless they are stopping oscillating, and that's happening at the scale factor of 10 to the minus 3. So that means that if you take about unity for today, and then you look back at the scale factor of 10 to the minus 3, that means that you would have to start out with about 10 to the minus 3 in terms of fluctuations in the density in order to form these structures as we see it today. And that's clearly in conflict with the actual expectation. So that means the delta that you start out with would have to be of the order of 10 to the minus 3. However, measured is, we know from the CMB that this value is more like 10 to the minus 6, 10 to the minus 5 in the peak-to-peak ratio. So that's clearly not sufficient. And another way of looking at that is that there must be something else which leads to the growth of the overdensity. And I have a plot here prepared for you, which gives you an example on how the growth proceeds for baryons. So let's assume you have baryonic matter. And what's plotted here now is the density contrast over the initial density squared, but the units are rather arbitrary. And then you find the scale factor A on the x-axis, and then you see that is at the time of the so this is one particular length scale that we're looking at. So that's entering at some point here the horizon, and then it starts oscillating. And these are the baryonic oscillations. You see this is a rather small mode, so it's a large k value here. However, there's no more growth in structure happening due to the oscillation at this point. And then the growth will only start again after the oscillations. And in principle, this line would then continue to go like this if you just have no other form of matter present. But if you have, in this case, dark matter around, which doesn't oscillate, so they will continue to grow structures. And then at the time of the decoupling, the baryonic matter falls and goes into the gravitational potentials that are formed already by the dark matter population. And that leads to this enhancement, the boosting, that let's call it, between the actual expectation when you take the CMB oscillation values and comparing that with the measured values today. And that's required. So we see that there must be some additional dark matter around. And so this is really a prime argument that you should take away from this. Now, the next thing that I want to look at for a moment is that how does actually then structure proceed to form? There's essentially two paths that you can take, or that you can imagine that the universe was taken. The one is that you have the large structures starting collapsing, and then you basically, well, you have then the large structures forming, and then the smaller structures would come out of the fragmentation process of these large mass structures. That means you start heavy or massive, and then you go down in the mass hierarchy to smaller masses, or you start out with small masses, which then start merging, and then they form larger masses. And in the gravitational collapsing timescales that you can imagine, or that you can calculate for gravitational stabilities, the actual timescale, that's the free fall timescale, scales with the inverse of the density, square root of. In principle, that's actually the same thing that we've been discussing in terms of the Hubble expansion. There you had also a similar relation. And this scale, this free fall time, sets the time over which a structure can form due to a collapse of an overdense region. And it turns out that this value is, if you just give it some numbers, it's about 600 megayears for masses of about 10 to the 12 solar masses. So that's a galaxy size mass range. And this scales with the inverse of this, the 1 over square root of the mass, and it scales with the radius, or the linear extent, or the size of this whole thing. And here I also choose now values which are typical for a galaxy. And so there you can expect that these galaxies can actually form within a time which is small against the Hubble time, that is the age of the universe. So these can form rather early. And the free falling time for a structure which is like the galaxy cluster scale, which is the largest clusters, or the largest sizes that we encounter, which are gravitationally bound and can form, and that's about 9 gigayears, so just a little shorter than the Hubble time. And there I put in a radius which is about this typical size for a galaxy cluster scale, so that's about a couple of megaparsecs. and a mass of about 10 to the 15 solar masses. So that's solar masses, and this goes also with 1 over the mass. That means that naturally, in this framework of gravitational stabilities leading to growth of structures, you'd start out with a small sized halos, which start contracting and growing in terms of their density. And then subsequently also larger structures can form, but the smaller structures in the meantime start already merging and forming then subsequently more massive structures. And this process can go on until today, which leads to more and more massive halos forming in our universe. Another way of looking at the growth, not in terms of the mass that's involved, that you can look at, is the linear size of these objects. And this has been commonly used in the framework, or let's say formally speaking, by taking this density contrast, which I introduced here. So delta is a function of a position, and in the isotropic and homogeneous universe, this is then a function only of some radial values r. So there's no deviation from isotropy here. And in this case, you can do a simple Fourier transformation. So this is then transforming this delta into the wave number space. And this is often then called delta k, where k is then a wave number, that's the inverse length scale. And once you've done that, you can introduce something which is called the variance at a given value of k. And that's then the average of the modulus of this Fourier transform. And this is often used as a measure to, or a way to looking at the actual way that structures form or evolve in spatial modes of k. And so large wave numbers of k indicate small scale structures, and vice versa. Small values of k imply large scale structures. And as it turns out, there is an interesting link between the way that structures evolve and form over time, depending upon the type of dark matter that you have, because we now establish that there must be dark matter around, which basically is the one which mediates here the growth. But here we're looking only at one particular value of k in this example. So the interesting story is, how does this actually happen when you look at different values of k? And this is often enough looked into this kind of diagram, where you plot the value of k as you observe it in today's universe. So this is then this variance k squared, and it's a value which you can plot now as a function of the wave number. To the right you find then the small scale, so this is 1 megaparsec inverse, so that corresponds to about a megaparsec scale. This is 10 inverse megaparsec, and that corresponds to about 100 kiloparsecs. And on the left side you go then to 10 megaparsec, 100 megaparsec, and so on. And when you now look into the initial spectrum, because you start out of course with some density perturbations, this is commonly assumed to have a spectrum which looks like this. So a priori you don't know this, of course. You only can measure the one p of k as today. But often enough the assumption is that there's a scale-free type power law, and in the most simple case you have something which goes with k to the power of 1. So the structures basically have this kind of slope, which is in a double log diagram. It's just a straight line which grows, or which has which increases with increasing value of k. And then you look at how this looks, how this would change when you, or how this values of p of k change in today's universe. Assuming that your dark matter is, for example, either a massive, non-relativistic, so-called cold dark matter particle, which is still moving with some velocity and therefore also is streaming and therefore smoothing out density perturbations that were initially there before they can start to contract and collapse. And this interplay between the smoothing, because of the streaming of the particle, and the gravitational inpull leads to a characteristic way that this power spectrum evolves. And so for cold dark matter, you find a moderate suppression at large values of k. So there's a turnover here. So you start out with this initial density perturbation, then you start having some smoothing out, and then also collapses leading to the formation of structures. whereas a light particle, which has a relativistic motion, even like a neutrino type dark matter, we call this hot dark matter, smooths out over much larger radii because of its increased velocity, and therefore this turnover happens a little bit earlier and goes even steeper. And so the observations can tell us whether this is cold dark matter or hot dark matter. And this is something where the observations tell us clearly that this kind of structure formation, where you suppress structure growth at small scales effectively because of the streaming properties, is not favored. And the observations clearly tend to favor something which is more on the side of the cold dark matter. We'll have a look at some actual observations just in a moment. So this is cold dark matter, which is written already here, smoothened because of the smaller velocity than the hot dark matter, smooths on not so strongly at large values. And here's now a measurement of this P of k in this. This is coming from a survey where the here you find this is the value between -1, so this corresponds to 0.1 here in the k space, and 1, and 0.5, so this goes from about here to 3 or 4, around about here. And then what you see is that this follows very nicely a best fit model, in which case this is assuming some cold dark matter. And there's an interesting modulation which you cannot see here, but which has to be present, because on top of the cold dark matter distribution, you do have these oscillations, which I talked about before. And these oscillations produce bumps which are characteristic and can be directly linked to the angular power spectrum that we see in the CMB. And these are the so-called baryonic acoustic oscillations, which we still see. So you see some evidence for these kind of bumps already here at this wave number. And this is clearly demonstrated by the data, and also is fairly well fit by a simple model in this case. Now, this is not enough to go really into this kind of high density region. We were still talking about the linear regime. In order to understand what's happening then on smaller scales, that is the nonlinear structure formation, you need to, in the end, ultimately crack it down with numerical simulations. I just want to show you a little bit about these numerical simulations, because they're very important tools in modern cosmology, and they are nicely and effectively combined with the surveys that people carry out. And I think this is beautifully highlighted in this kind of comparison. I show you now here in this plot two data sets. One is a real data set that's in bluish and magenta, where it's plotted now the distribution of galaxies. So each little blue dot is a galaxy that has been observed in a slice, that is, you look at a particular band and write ascension and declination, and then for each of these objects its image position and also its redshift through its spectrum. And in this case, then you start picking out these clear structures which are filamentary, when there's also some voids where there's underdensity of galaxies in between. And these structures are kind of characteristic for structure formation in cold dark matter. And this can be very nicely matched with mock data sets where the distribution of matter is simulated following the approach that you put in test particles, which have masses of the order of several 10,000, 100,000 solar masses, and these test particles then interact gravitationally with all the other test particles, which is numerically a tough problem to crack. And then you follow dynamically from an initial fluctuation spectrum and density, which is like this Harrison-Zeldovich P of k goes with k spectrum, how this evolves over time. And then in the end, ultimately, the dark matter distribution is settled in a characteristic structure, and then they populate these density distributions or density structures with galaxies. And then in the end, you can sort of do a mock survey. That is, you do an you simulate your observations in terms of sensitivity. That is how far you can go to observe these. And then you get these kind of mock data sets, and it's really kind of fascinating to see that you wouldn't be able, unless I tell you that the red stuff is actually something which is simulated, and it looks very, very similar to the actual observations. It's partially because they picked then in the end particular positions in the simulated space which resemble closely what we do observe. But in the end, it's nothing particular characteristic about these observations that we do, which cannot be found in these simulations. The simulations cover a much larger volume than what we can see in our surveys, and I just pull in here a figure where this is better demonstrated. So this is now a slice in a three-dimensional simulation space of such an n-body simulation. This is the so-called Millennium Simulation, where now the density contrast of dark matter is clearly shown in this color scale, and what can be seen is that there's this filamentary structure, which is very characteristic for this kind of structure formation, where you have voids and high density regions which form like a web-like structure. But this is of course three-dimensional, keep in mind, this is just a slice going through this. And now basically this kind of simulations take one position like here, and then you pick a position and simulate these kind of mock data sets. These simulations are dark matter only, in the sense that actual galaxies do not form here. It's just the dark matter which grows in galaxies, which grows through the gravitational stabilities. And there's not much additional physics, which is important at some point, because ultimately in the central parts of the galaxies you're dominated by baryonic matter. In our case, for our galaxy, it turns out that where the sun is located, we have roughly speaking about the same amount in dark matter present as in stellar and gaseous matter on average. Clearly, when you're down here on Earth, you're always dominated by baryonic matter. But if you take, for example, 100 parsecs or so cubed region, and then you just average out stellar matter and gaseous matter, then you end up having about the same dark matter content in that box as you have in normal baryonic matter. And if you go closer to the galactic center, the baryonic matter dominates. Whereas if you go further out, it turns out then there's the dark matter is dominating. Just as a final point, because this is not the end of the line of these simulations. Simulations are starting to become more detailed in terms of the physics that is included. So it's not just gravitational interaction, but the more recent simulations are taking into account that there's stars forming, there's a heating process, there's baryonic feedback, there's black hole formation also. So these additional effects are quite very important, and ultimately can be used also to compare the data more clearly with the observations. And I find also this is a very impressive result of more recent simulation. This is the so-called illustrious simulation, and this was a recent Nature paper where these individual snapshots that you see here are now galaxies forming over the lifetime of the simulation. So you both can trace the evolution as well as the type of galaxies that you form, and you find elliptical galaxies, irregular galaxies, you find disk galaxies, and these galaxies are not observed this way, they are basically simulated that they form this way. And this is really, really fascinating. And also in this case, they've put together back to back, so this is the left panel B and the right panel C. I don't actually know by heart which is which, but one of them, I think the right one, is an observation with Hubble telescope staring at a small, few arc minutes patch in the sky for a very, very long time, and therefore going quite deep in terms of the galaxies being observed at redshifts up to 6 and 7. And on the left side, the same kind of data has been simulated. That is, in the large-scale simulation, they just basically install an observer somewhere in this simulation, which looks outward and then observes these galaxies, including their colors, including their morphology, including their redshifts. And this is really, really close to the original. And that tells us that the simulation takes into account quite correctly many of these effects which play a role. And to summarize this, so this is of course beautiful pictures, but in the end scientists are more interested in quantitative comparisons. I just want to show you this plot, which shows now in a slightly different way. So this delta squared is pretty much this P which I was explaining to you before. So that's the structure, the density contrast as a function of K number. And so in this case, slightly different weighted here. That's also it's a squared value. So in this case, what you see is let's compare the light blue line. That's the illustrious simulation that I was talking about, taking into account only dark matter. So there's no baryons, there's no stars, there's no galaxies forming. It's just dark matter contracting. and then you end up with a function of structure which at large values of k starts to turn down actually again, whereas baryonic components lead to the black curve. So there you have an excess density contrast of about an order of magnitude in this case, and that's really related to the baryonic mechanisms which are absent of course in dark matter, so that you can heat up the material, and you have also black holes forming, and this leads to quite substantial differences in the growth of structures. The bottom line, to summarize this very, very briefly, this was what I was saying at the beginning. Structure formation is to some extent well understood if you add an additional agent, that is the dark matter, which leads to the formation of the structures as we see today. And the detailed understanding of this comes from both observations, as well as observations I showed you this example here, as well as simulations of the structure formation, which can be calculated numerically and follows dynamically both a large time range that you can cover in evolution, and as well also a large range of different masses that can that are sufficient now to resolve individual galaxies quite nicely.